Hello, uh, welcome back. This is Alan, and this would be lesson number 15 in this tutorial series, which has reacquired its original name, uh, Effective Programming in C++. I think I'm on take 3 of this one. Uh, Having a little trouble explaining one particular thing, but hopefully it'll go better this time. Now, there was something that I keep failing to explain correctly, I think, and it's two things that I'm messing up on. Let me try again. This is just going back to the last one. The last example was this. Okay, and what we were talking about was, so this was the last example. And what we were talking about previously, so now I've got it upside down. We'll do it right side up. First example was this. Okay? And the main question was this. How do we do this? Food. And we came up with an answer. The answer was to get something into AX, put something in AX, and then employ the regular machinery, which we invented as well. That puts whatever's in AX into I. And that machine looks like this. The one we invented. I happen to be at 300. Say, and whatever the value was. AX, sorry. So here, this is a literal. Why don't I make? Oh no, that's the address. This was putting the address of I. I think we use D actually, because it's a destination. Store AX at DI. Not in DI, but at DI. You understand the difference. Okay? So, what we said then, okay, well, all foo has to do is get the value into AX, and then we can use our little AX machine, call it the AX to destination machine or something. Our machine. Our assignment machine. From AX. Okay. So this is the thing that we're given. We know that we decided perhaps that this is the way that we are going to assign things into I, or anything in the left that's an integer anyway. And if that's the case, it doesn't have to be, but in fact that is the one that's used, AX, then foo does not need to know anything about I. All it's got to do is get something into AX, and then we emit this code. The compiler will emit this code following that procedure, and it'll work like regular assignments. So that means that this becomes exactly 100% the same as that. And I wanted to give an example of food. And this in fact was my example. Unfortunately, I should have put I on the left here because I switched it. Instead of storing a value in I invented a new variable called J and stored something in there. But it's completely symmetric, so it's the same thing. What we did was we took the right hand side, found a way to get it into AX, and then we used this machine, except instead of 300 it was 400 because that was J. Okay. Now, I hope it's clear that that there was a point to that whole last example. The point was that I was trying to give an example of this foo. In that case, it was memory-to-memory assignment rather than a literal. But the literal case, here's the literal one. The literal case was moved into AX. The literal number 6. Then moved into DI, the address of I, and then moved into position DI, so dereference AX. Now, I guess there's a little bit more that can be said about this. For one thing, this kind of explains, maybe not, but it sort of gives you a hint anyway as to what they mean by when something is an L value or an R value. 6, okay, is a literal number. I can't assign it in. I can't change 6. 6 means 6. I can't assign 6 another number. It's already itself. You can't say, 6 equals 5. This type of function that stores values in AX behaves just like the number 6 in that it's a literal. I can't assign, anything to this because all it is it represents a number just like 6 does. It doesn't have a way of becoming anything else than what it is. These ones, though, can be reversed. This example was completely symmetric. We could have put I on this side and J on this other side. So there is a slight difference between this and this. It's not exactly the same. Anyway, I wasted a lot of time on that. I've done it again. Right. Okay. Now, I'll try to do this quick. I want to explain two things. One, the calling part and the returning part. And two, the stack. Now, those two things are in fact almost the same subject, if not identical. Because the way you call a function is by using the stack. Well, the call itself, it wouldn't have to use the stack. You can use the jump. But a call which is a built-in operation in the machine called call. Let's say it like that. This thing does something to what's called the stack. I'm going to put two instructions here. And I'm going to go over to 200. And I'm going to put in the other instruction that goes with this instruction called rest for return. And I'm going to trace through this. And first, without explanation, I'm just going to show you it works. Okay. So here's the instruction. I trace through. It jumps over to 200. There's an RET there, and it comes back. Okay. Now, how did it do that? Obviously, I don't want to go through that one in 20. Obviously, the value where it came back to 103 had to go somewhere. There's nothing supplied to RET. It's just a single byte command. So the value of the return address had to have been copied somewhere. And the processor does that automatically, and it puts it in a special place. And that special place is a position on what's called the stack. I'm going to show you again. I'm going to run through it again. Trace. And now instead of returning, I'm going to dump 2 bytes, and I'm telling you right now that those 2 bytes amount to the number 103. F-E-E-D. Now, F-F. There you go. See? Insanity land, we read it backwards, 103. So that's where this guy got this value. Now how did it know to look there? Well, look here. FFEC. This thing, now you know what this S is probably about, is called the stack pointer. Okay? And what it points at is the last thing that was what they call pushed on the stack. Remember we did these push AX and push BX, all that stuff before. Those instructions are instructions that put things in this memory area on the stack, but they would be they go down. I'm going to show you that in a minute. You can see that the initial value, FFEE, before the call, is bigger than it is now. The value changed by -2. So it went down by 2. And that's what always happens when you push. A stack is a thing like, a stack of trays, if you ever worked in a restaurant. It's a thing that grows as you push more things on it, but instead of growing up, it grows down. That's the convention. It's easier. You put the stack far, far away, and it grows down, and hopefully you don't end up colliding with it. Now, so that's all there is to it. Now this return instruction is very similar to a pop. Remember pop? Pop takes something off the stack and then increments the value. So this return is a pop, but it's sort of a pop into IP. And that's where we are at the moment. Trace through it. Stack goes from where it was, up by 2, and we're at the end. And that's all there is to a call, and all there is to getting back. And the reason why I'm just telling you the answer in this case rather than what I usually do is because there's no other way to do it. That is, we have no access to this IP thing. And the last time I explained it, but I'm going to leave it as a puzzle for you. Why is this impossible? Why is that an error? Why is this an error? These are all errors. Anything you try to do, anything you try won't work. Error. The processor will not let us look at this value. And there's a definite reason why. And that's your puzzle. I'll answer it next time. Okay, now, the next thing is, how do we, now that we can call a function and come back, how do we send information to a function? What's the usual way that it's done? We've seen examples, in fact. Here's a perfect example. These are functions. In this case, we're using the registers. So one way to pass information is to use the registers. But, of course, eventually you might run out of registers, and you have to find another way. Well, it's probably not surprising that the way that people decided to pass information to a function, especially in the case of C, this type of thing involves pushing things on the stack. Basically, something gets pushed onto the stack, and foo here knows it's on the stack because we told it it's on the stack, and somehow retrieves it. So how is the next part? I'm going to go back to 100, and we're going to send our 200 buddies a little message. We're going to do this. Okay? Alright, now you just have to think of something to send over there. How about 1, 2, 7, 8 or something? Now, problem with the caps. First, I'm going to put the value I want to send into register. Which one do I want to use? I don't know. DS. I know I can push registers on the stack. And I'm going to push it on the stack. Before I call the function, I'm going to clear dx out again. That way, you'll know for sure that the only way that our friends at 200 could ever get the value 1278, which is now gone, will be from the stack. Now I'm going to call it, and when it comes back, we'll quit. So now let's go over to 200, and let's think. This is what we've been told, and we're trying to compile it. Somebody's written this code down, so we know that we've been called, and we know there's an integer value on the stack. How do we get it? Okay. Well, we know that there was a call. They had to call to get here. So therefore, whatever the stack pointer is pointing at is the return address. We don't know what it is, but it's going to be 109. So we draw a diagram of the stack. This is what, on entry, this is what we know. Let's set the bar here. That the stack pointer is pointing at a return address. Okay. That's why they call them pointers, because they point just like you point with your fingers. So whatever is in SP, the address pointed to by SP is the return address. But that's not the one that we want. We want the thing that was pushed before the return address was pushed. Now where is that? This is one of those things where you've always got to think upside down. The return address, okay, was pushed, no sorry, the value, the DX thing, was pushed first, and then the return address. So since things are going downwards, then the value that was pushed before is here. But stack pointer is pointing here. So in order to get the value, all we've got to do is add 2, because we have 16 bits. World, it's 2 bytes for a return address. So this is SP plus 2. So all we got to do is find a way to get square brackets around that expression, and we got it. So how do we do it? Well, as usual, you're not allowed to use SP. There's a reason behind all of these things, and I'm not 100% sure why certain things you're not allowed to do. But remember, this is a device. It's electronics. You can't do anything your mind can think of. There are restrictions, and one of those restrictions is, you can't go from an ES to, you can't copy ES into DS, for instance. It's not allowed. It's not because it's theoretically impossible. It's because it's just not wired that way. And one of the things we're not able to do is what we want to do. So we want to put it into AX. We're not allowed to do the thing we want. That's what we want to do. Error. And the error is you're not allowed to use SP. Okay, no problem. We'll use a different register. Now comes the point where you go through all the experiments and then you eventually find out which is the one that works. And the one that works is this one, BP. Okay? It turns out that BP and SP are specifically designed for stack. So square brackets around a BP does the same thing as square brackets around a value, an SP value. So all we got to do is get this SP into BP, and then we can use the brackets. So it's very simple. All we do is we put into BP the value from SP, and it's okay with that, no problem. And then move into what we want to retrieve the value, AX, let's say, BP plus 2. And it's okay with that. Now, I don't know what we want to do with AX, but we just want to see it go there, 1278. Then we'll return, and there'll be one more thing, and then we're done. Alright, now we got to get back to 100. Everything's clear. And we're ready to go. Here goes. Now, just take note of where we started, especially the stack. Okay? Now, nothing's happened to the stack. dx is modified like we wanted. Now I'm going to push it. Stack pointer has gone down too. We expected that because we did a push. Now I'm going to clear out dx. Otherwise, everything else is the same. Now I call. Stack pointer went down again. Another 2. So, in fact, in this case, now wherever we're going to go back to is at the address pointed to by the stack pointer, just as before, FFEA. And we can dump it. $109. That's exactly correct. And if I add 2 to that, I'm going to dump it. There's our 1278. And that's the one we want to retrieve. So we're putting that, first we're taking the SP, putting it into BP. It's even showing us. That's adding to the BP, and then put in the brackets, will give us 1278. So, and now we can store that in AX. It's been stored, and we turn back, and we're done. Right? Almost right. Here's the problem. This thing started out, well, it's gone now, as FFEE, but now it's saying FFEC. So we haven't cleaned up enough. We missed something by 2, and it should be pretty clear. We did two pushes and 1 pop, basically. So we're missing a pop. And there are 2 ways that this problem is solved. It's not a problem. 2 conventions in which the stack pointer, after a function is called, is reset to what its original value was. And the 2 conventions are, one of them is called the C calling convention, and one of them is called the Pascal calling convention. In the C calling convention, it's our job, the 100 guys, to clean up this mess. In the Pascal calling convention, it's the 200 guys who are responsible. So, quitting the program now, although it will not cause any damage, is not the next line that we should have here. The next line should be clean up the stack. So I'm going to overwrite this with what should be here, which is to add to SP 2. And then nobody can get mad at us quitting after this point. So I trace through that. Now we fix this stack, and then we're done. So that's what they mean when they say C or Pascal calling convention. And I'll let this be another puzzle for you to think about. In C, in C programs, values that are pushed onto the stack are pushed in the reverse order, that you see them listed in the C script. It wouldn't matter. In the Pascal calling convention, they're not. They're pushed in the same order you see them listed in the call. And I'll leave it as a puzzle for you as to why do they do it backwards, for one thing, and for a second, why is it better to push them backwards? I don't, actually, I might be wrong about Pascal. They may push it backwards too with Pascal. The most important difference about C calling convention is who's responsible for cleaning up the stack, and that's the caller in C. And there's a reason too why that has advantages over the Pascal calling convention. And I'll let you think about it. Why, what the advantages are, and why some people would prefer it. Okay, well, this program has terminated, and so have I. See you next time.